Hello and welcome. I'm Shadow of Shadow Gaming, bringing you Programming with Shadow, episode number 73. In today's lesson, we are going to be talking about heaps, and in particular, a minimum heap. So we've sort of looked at heaps in the past. We did a light heap implementation for our heap sort back, I don't even know how long ago, probably about episode 60, so 13 episodes ago. So a heap sort is using a structure called a heap, and we're going to see today a heap's a binary tree. So it's a special kind, however. So unlike the binary search trees we've used, with a heap, we don't maintain an order between the left and right children. We only maintain an order between a node and its children. So, for example, a max heap, every parent is greater than or equal to its children. For a min heap, every parent's less than or equal to its children. We're going to implement a min heap today because that's the one I've actually used the most of. So we'll implement it. The one thing to keep in mind with a heap is that it's not sorted. However, when you get everything off the heap, everything's sorted. So here, if we have a tree that looks like this, we'll have 10, 20, and 30. So that one's a minimum heap. So even though the things on this level are odd, like we might, with the other heaps, we might have it down this way instead, so the 30's on below the 20. For a minimum heap, it doesn't matter. And we'll see why as we go it, but all that matters is that 10 is less than both of these. So heaps have another rule. So with binary trees, we've been able to make them and not have them a full tree. Heap's not that lucky. So with a heap, you must insert from the top. So the next insertion would be here. And then the next one would be here. I don't know. I'm doing these, but that's not making sense, but there. So as you fill up, you have to fill left to right. So you fill top, left to right, left to right. The reason you do that is so you can store it as an array. So when you do it, you're just storing it in an array like this. So, and this ends up working out. So here, if we, let's write the indexes. So this is index 0, 1, 2, 3, and 4. So these are the indexes. So we have formulas we can use that give us those values. So parent equals I minus 1 divided by 2. This always just works out because of it's a binary tree. So let's say we're looking for the parent of 20. So for 20, the index is 1. So we get 1 minus 1, 0 divided by 2 is 0. So parent equals 0. Look at 40. The 40 gets index 3. So 3 minus 1 is 2 divided by 1 equals index 1. So the parent is 20. So easy enough. So there's a formula for a left child as well. So left equals, let's make sure I can do this, 2 times index, and it's just plus 1. Plus 1. Right's going to be very similar, 2 times index plus 2. All right. So let's try this. So let's say we have 20. So it's index 1. So left child is 2 times 1. So 2 times 1 is 2 plus 1. So 2 and 3, and we get 40. Same thing here. 2 times 1 is 2, plus 2 is 4. And as we scale out to this array to bigger and bigger values, these formulas just keep working. And that's where a lot of the heap gets its power, is it's using an array as the background. We're going to use a list for our implementation, but doing it like that gives you the power to you're getting a lot of the list access or the array accesses, because anytime you need to find the minimum value, you just take the first value. Notice that I said there's no searching or no sorted. It's not sorted. That means we're not going to be able to actually search. So one of the values we're going to have is a peak, which lets us see the minimum value, but we're not going to have a search to go find the value. I guess technically you could add one, but it's going to be you're going to have to go through everything, I think. We'll see deletion. It's a little complex, but compared to the red-black tree deletion we did last time, delete's not that complicated. So let's say we want to insert a value. So we'll use this heap since we've already got it. So let's just copy this down below. All right. So now let's space this out a little bit. And we insert a 5. So now the heap property is that every parent must have smaller, or be every parent must be smaller than its children. This is in violation. So we've added it. We added it to the last index, by the way. So 5. 5 and 5 just so happens to work out. So we've added it to the last index. So now we need to do some cleanup. And what we're going to do there is we're going to compare it with its parent. The parent doesn't meet the heap property. It's not less than it. So then we are going to backspace that. We are going to do this again. But this time we're going to swap 30 and 5. So we swap the two positions. Now we can check if this is still valid. So this becomes 30, this becomes 5. We made use of indexes. We'll use that swap function we wrote for the sorts earlier. We'll rewrite it for this, but we'll use it again. So now looking at this tree, now 5 and 10, so the property's still not good. So then we repeat that process. We do it again. Here, let's stop this. So we swap them again. So now 5 and 10 get swapped. And now 5 and 10 have been swapped. So now it looks like this. And now the heap property is reestablished. We get 5, 20, 10, 40, 50, and 30 in the array. And see, there's not a lot of sorting that's happened there. That doesn't look sorted, but as we do the array operations, we'll see that it does happen. So what did we notice with that, though? We're only concerned with one branch of the tree. And because the tree is a full tree, we get log in operations. So insert is big O of log n. So another operation we have is peak. And it is big O of 1. So it's just always read the first value of the array. So there's some condition there, like what happens if it's a if the array is empty. And I'm just going to throw an exception. You could do something else if there's something else you want to do there. So the last operation we'll look at is remove, and we'll we'll come back to what big O it is. So let's use this tree here. We'll use the one we just made. We'll grab the indices as well. All right. So what we do here, we move to the last element. So we'll be able to find the last element of the array. We move it to the root. We save off the root somewhere, by the way. So we'll save it off so we can return it. That's how I'm going to handle it. Wait a minute. Let's do this. There's the first operation. We start there. Then we swap 30 and 5. Well, we don't even swap. We move it. So it's more like that. And 30 or 5 is now somewhere else. It's in a minimum value somewhere. And we don't have to worry about that index anymore because it was removed. But now the heap property is violated. So now we have to manage that. So now we have to find which child it is. So we have these left and right ones. So we'll grab the values from both left and right child. We'll say, okay, which one's smaller? 10's smaller. So we will swap the place of the smaller child. So then we get 10, 30 here. And then we get 10 and 30 here. And we have our, this is back to us, a heap, a valid heap. So that's all all we have to do, and we did a deletion. Notice what it did there as well. So we only concerned one side. If it had been over here, it would have been the same thing. We would only went down one side. Because we're maintaining the full tree here, notice it added it to the end, deleted the last element, and we're still a full tree. So insert will just keep adding there. So that's all there is to it. And that gives us big O of log n as well. So, well, so it gives us so the way you can use this, you can use it to find a minimum. You can use it for a sort. You can also use it for a priority queue. I think we've used that before. In fact, I think we did back many lessons ago in the shopping line or movie line simulation. I think we used priority queues then. A minimum heap can be used as a priority queue. And that's actually what the .NET implementation is, I believe. So some of the So what it gives us is that you can always find the smallest or minimum very easily, and you can keep pulling off smallest or minimum. And it doesn't have a lot of the problems of some of the other ones. So if you have a list, insert's easy. You just insert it and it's one, but then to find it, you have to search through the entire list. If you sort the list, then insert becomes big O of n. You might have to deal with the whole list. But remove the smallest, you know which one's sorted, so it's constant time. Heap doesn't do either of those, so heap is in the middle on both of them. It's log n, so it's a little faster on the faster operation, but it's a little, or on the slower operation, but it's a little slower on the faster operation. And it gets peaks so you can see what's there. And that's where you'll see the use of though is when you're needing a lot of operations. So let's build up our heap class, and we're going to do a min heap, like I said. So we'll have, let's start a new project, add new project. We will do a min heap. There we go. So I'm just going to grab this, I think. Yeah, I'm just going to grab this, and we'll just grab this part of it. So this will have a lot of errors. We'll fix those in a minute. So instead of a red black tree visualizer, it'll be a minimum heap visualizer. Insert, instead of search, we will have peak. Instead of delete, we will have remove minimum. If I can spell. Now we will have a print tree. We'll have a print heap. We won't have the print in order. So let's get rid of print in order. And we'll have a return. So that's pretty much what we set up. Probably here we'll call this min heap, and we will call this Alt Shift semicolon to select all. I'll call this heap. So instead of this, we're going to have we'll have a console dot write line heap dot to string. So we'll print that. That'll be our print method instead. So anywhere we've got print, we'll just swap those out. Delete will be remove min. And it'll return a value, so we'll say int min equals that, and we'll just do CW remove the minimum value min. I think that's what I want to do there, and here value. I don't think that makes sense. Let's do this. Let's do console.writeLine. Maybe minimum value is heap.peak. Like that, I believe. I think that has us set up how we'll want to do this. Yeah, I believe that's good. So we'll try it out and see. What is this like? We are missing one more brace at the bottom. There. So let's implement the min heap. So min heap. Let's do public class min heap. There we go. So we will have a insert method, public void insert int value, throw new not implemented exception, public int peak, throw new not implemented exception, and public int remove min, throw that. We'll also have a toString, so let's do it. Public override string to string. And for this, we can go ahead and do a return. So what we're going to have here, we'll have a $this. So I'm going to print this as an array, so we will do that, and we will have the string.join. We'll connect it with that, and we'll need some value here to put it in. So let's have a list of int heap equals that. And we will just say heap, and that should be our toString method. So that, there we go. That should be what we need for the values. Remove min, is that what I called it? It is what I called it. Doesn't take anything. Here. Okay. So that gets us this building again. So let's move this to its own file. And we'll move this over here. Let me open that file we just added. There. And let's implement. So the first thing we're going to implement is those helpers we looked at. So we're going to have a public static int get parent int I I minus 1 divided by 2, right? I minus 1 divided by 2. We'll have a public static int get left child int I. This is just 2 times I plus 1. It's trying to help me if you're not going to help Copilot. Static int get right child int I 2 times I plus 2. So I think those will be those helpers, and let's add this. So we'll add public void swap int x int y. So we'll do heap at x comma heap at y gets heap at y comma heap at x, like that. So first thing first, control alt shift dot dot dot. I'm going to make all these private. We're not going to need them outside of the class. So those will be our helpers. Here we can make this one expression body as well. All right. So one more thing we're going to add. Let's add a property up here for count. Public int count. This is easy. It's just heap count. And we'll see we're going to use it internally as well. In fact, I don't know if I actually will use it externally. But yeah, there we go. So peek is easy. So peek is just this. So let's just return count equals 0. Throw new, let's do invalid operation exception, I guess. Heap is empty. Or heap at the first value. So the minimum is always at the first value. So that one's easy. And we can make this an expression body member as well. On the next line though, so we can actually see it there. So that would work. So let's do insert. So our insert algorithms, what we did here, we inserted it to the last position and then bubble it up. So insert at the end of the heap array. So here we'll just do heap.add value. All right. Starting from last entry. So we'll have a var current index equals count minus 1. And now we want to bubble up the value until the heap property. This is that all parents are smaller than the children is valid. So I'm just going to do this while current index is greater than, not equal to 0. Then var parent index equals get parent of the current index. We'll get their current index as parent. And then if heap at parent index is less than or equal to heap at the current index. So if it's less than or equal to, we are done. We can break. Else we will swap parent index with the current index. And then current index equals parent. And there we go. That should be an insert. So that'll cause us to bubble up as we go. So we grab the parent, We check if they need swapped. If they don't need swapped, we're done. If they do need swapped, we swap them. We make this one the current index, and we continue on. So we'll grab the parent again, which will be this one, and go back through and do it again. So that should be insert. So that was pretty, compared to red, black, or AVL tree insert, that's not that complex actually. So remove min is a little more complex, but it's still not a ton. So let's do this. So we will have if count equals 0. So that's using that count we used before, just like we did here. So this is just a guard. If there's no values, we are done. Else, we need to save off the minimum value. So int min value equals heap at 0. Here, we should do this. Let me come back up here to these. These two vars here are both ints. I don't know if I've been using var in these lessons much yet, but either one would be valid here. They are ints though. So next step, we want to move the value to the, now move the value at the end of the heap to the front. So we saved off the first value. Now we're just going to overwrite the first value with whatever the last value is. So int last index equals count minus 1. So then heap at the first index gets whatever's in the last index. So we set that value, and then we remove at last index. So we remove the last value in the array. I'm saying array, we're using a list, but it's just an array that expands. So the last value in the list there. So now we want to sift down larger values. You may see that terminology, or bubble up smaller values. You could see either one of those terminologies. So now we'll get the current index. Index equals 0. Now we just need to loop for a couple times. So while true, loop till finished. And out here, I'm just going to return min value, so I don't forget it here in a second. I could see me forgetting that one. So now we want to grab the children. So the left index, get left child of current index, int right index equals or C of CI. There we go. One more index, we need the smallest equals current. So currently the one we're looking at is the smallest. We need to update that though. So if left if left index is greater than the count, so we need a guard, and heap at left index is less than heap at smallest. So smallest for this one's the shortest. If this is the case, then smallest index equals, I didn't call it index. Smallest index equals the left. So it gets the left index. Is that not right? Wait a minute. Close. There. So there, if the left index is smaller, we set it. So it says it's unnecessary, we'll make it necessary. If right index is less than count, and then heap is less than right index, less than heap at smallest index, smallest gets right index. I wish that would go away so it would quit interrupting us. So here, it's either going to be the current if left wasn't smaller, or left if the left was smaller. So what this does is it gets us the smaller index. So now we have the smaller index. So now if smallest index is the current index, so this is the one we saved off beforehand. So the one we saved off at first, so we're saying the 0 is already the smallest. So if it is, we're done. We don't have to do anything else. Otherwise, we want to swap the current index with the smallest index. So this will get it on whichever side's the smallest. And we're almost done. So the last thing we want to do here is update the current index with the smallest, which is what it wants us to do here. So there we go. So that's a remove minimum function. So it grabs the two children, picks which one's smaller, swaps the positions, and then sets it to this one, and then checks for their children. And in doing so, we maintain our heap property. So this should be all we actually need to implement for a heap. Let's go test it out. We can make this read only. Let's do that. Is there another option there? Yeah, it's down here. There. Any other tips that it wants to give us? Not really. You could put these in parentheses. It's not required. It's not useless. Not required. Your call on that one. I'm asserting these two are the same. It'll evaluate all of these before it returns the value, basically. I guess technically you could also do this just so you know that the 2i happens first. I personally don't care. I think either one of them are fine. This one you need to do it in this order, otherwise you get 1 divided by 2 first. But that's our min heap. So let's give it a try. We will use this example here. Let's set the value. We want to use the min heap. I should have called that min heap visualizer. So let's run it. All right. We want to insert a 10, insert a 20, insert a 30, insert a 40, and insert a 50. So that gets us an array that looks like this. So first thing we did was add a 5. There, it went through all these steps and ended up 5, 20, 10, 40, 50, 30, just like we expected. So if we peek here, we should see that we found a 5. Now, if we remove that value, we should get back to this order of a heap. So let's print heap just to make sure we know what the order is. Notice I've got the numbers mixed up. I wonder if 6 is actually exit. We'll fix that in just a second. Let's remove the minimum though. We removed 5 and we got our heap as we expected. So let's remove another one. Let's remove 30. Oh, that's not a valid choice. 3, 30. Oh, it's a heap. I can't tell it what it's removing. It just removes the smallest being done. So there we go. And if we remove 50 now we have an empty heap. Now if we remove it, we should crash. And we do. Good. Is 6 exit? 6 is exit. Let's fix that. Should be 5. I guess technically it was fine, but we'll make it 5 just for consistency. But that's our heap. So code-wise, I argue that this one's simpler, but you don't have any searching. So if you're needing searching, it is not the data structure for you. If you just need the smallest value, there's where it shines. Let's see. We compare this with the node. We compare it with our tree here. So insert node here looks like this. So all this code was insert. Here, I think all this is insert too. Yeah, all that's insert. So this is a much simpler insert. So you can tell it's not doing the same kind of logic here. It's not trying to keep the search good. It's only trying to keep the minimum value good. And that's where you get your usefulness sometimes. Peek and search. peak is very simple. And the minimum value is also very simple. Delete here is pretty large. Doing it like this is not as complex. So that's a min heap. So that's all we're going to do today. So very short lesson, but that's what I wanted to cover. So I would say I will say you, as I said, you can do a max heap. If you want to do a max heap, you just swap the logic here. You want to have every parent to be larger than the children, and you do that route. And instead of finding the smallest here, you would find the largest. So just a little difference in conceptualization, but it'll be about the same code. That's, as I said, that's all we're going to do. An upcoming lesson, there may be one in between this. I may do another side one. The upcoming one's going to be a hash code. It might also be time for us to do some programming and actually do a little project with some of these data structures, some of these tree structures. But a hash table or hash map, however we're going to call it, is another data structure, and it has a C# analog. Min heap has a C# analog. If you use the priority queue class, it's basically implemented as a min heap. So that'll be for upcoming lessons, though. So we'll call it here. So this has been a min heap. So thanks for watching, and have a wonderful rest of your day.